To process the massive demands of generative artificial intelligence, modern data centers must execute trillions of matrix calculations every second. This chart compares the inference throughput of two recent GPU architectures running large language models. The older Ampere A100 sits at roughly 130 tokens per second, while the newer Hopper H100 pushes well past 250 to 300 tokens per second. Generating tokens at this speed requires a physical reorganization of the internal logic, as simple transistor scaling is no longer sufficient to sustain these workloads. Before reaching these throughput numbers, engineers had to solve two distinct silicon-level constraints. The first was inside the processing cores themselves, a rigidity in how the streaming multiprocessor, or SM, allocated its internal data paths. The second constraint existed outside the compute cores, the severe latency penalty incurred when moving data between the host CPU's memory and the GPU's memory. Traditional software-managed memory systems require data to be explicitly copied back and forth. If the GPU's cores finish their math before the next batch of data arrives, they sit idle, they starve. To understand how modern infrastructure actually functions, we have to look closely at these two solutions: the evolution of the SM data path and the shift toward hardware-coherent unified memory. Solving these two hardware constraints turned the GPU from a graphics rendering tool into the primary compute engine of the modern data center. At the silicon level, actual GPU computation happens inside a module called the streaming multiprocessor. This diagram shows the internal structure of these multiprocessors. Look at the Turing architecture on the left. Its CUDA cores are physically separated into two distinct pipelines, one dedicated to 32-bit integer calculations, IM32, and the other strictly for 32-bit floating-point math, FP32. Graphic rendering relies almost exclusively on floating-point arithmetic, running the FP32 silicon at maximum capacity. But as workloads shifted toward artificial intelligence, demand for integer calculations spiked. In a rigidly split architecture, if a program primarily requests integer math, the dedicated FP32 cores sit completely idle. The middle panel shows the interim solution used in the Ampere and Ada architectures. Engineers modified one of the data paths so it could process either floating-point or integer instructions, effectively sharing the load. Now look at the right panel, showing the current Blackwell architecture. The physical division is gone entirely. In this unified structure, all 128 cores in the streaming multiprocessor can dynamically execute either floating-point or integer instructions. A calculation no longer has to wait in a queue for a specific physical lane to open up. The hardware routes the instruction to the first available core. By unifying the data path, the architecture eliminates idle silicon. Every core remains active, fully utilizing the chip's physical area. Alongside standard CUDA cores, modern multiprocessors include tensor cores. These are highly specialized units designed exclusively for matrix operations, the exact math that drives neural networks. Early tensor cores in the Volta architecture calculated at 16-bit floating-point precision. Today, architectures feature a transformer engine optimized for ultra-low precision formats, scaling down to 8-bit floating-point, or FP8. By halving the data precision from 16-bit down to 8-bit, the physical size of the data is cut in half. Because the matrices take up less space, the hardware can fit twice as many of them into the same calculation cycle, doubling the raw operation throughput of the silicon. Efficiency gains extend to the data layer through a feature called fine-grained structured sparsity. In many AI models, a large portion of the dataset consists of zeros. Sparsity allows the hardware to simply ignore zero-value data entirely. By filtering out empty data before processing, the system compresses the workload and acts as an additional multiplier. There is a critical caveat. Packing more calculations into a single clock cycle means absolutely nothing if the memory bandwidth cannot deliver data fast enough. This surge in compute density makes the delivery speed of the memory system the primary constraint on total performance. When a high-speed processor tries to pull data through a narrow, poorly managed connection, the entire pipeline clogs. This is the memory wall. Even the most perfectly unified streaming multiprocessor will stall instantly if it is starved for data. To understand how systems deliver data, we have to look at memory tracking. Processors map data using virtual pages, which point to the actual hardware locations called physical pages. The index linking these two is stored in a fast cache called the translation look-aside buffer, or TLB. If a processor looks for an address and it isn't in the TLB, it causes a miss. On a GPU, a TLB miss carries a significantly higher performance penalty than on a CPU. This diagram shows a software coherent memory system. Notice that the CPU on the left and the GPU on the right maintain completely separate page tables. They do not naturally share a map of where data lives. If the GPU requires access to data currently held by the CPU in this isolated system, it triggers a cascade of delays. The system generates a page fault. It has to invalidate the current table entry, physically migrate the data across the PCIe bridge to the GPU, and then update both tables to ensure coherency. Furthermore, data in software coherency moves at massive page size granularity, causing huge latency spikes as the system shuffles heavy blocks of memory. Software coherency forces heterogeneous systems to waste massive amounts of their operational time managing memory movement rather than executing actual math. The modern solution to this gridlock is hardware coherency, utilized in advanced systems like NVIDIA Grace Hopper and Linux environments with heterogeneous memory management. Instead of maintaining separate maps, a hardware coherent system relies on a logically combined page table shared perfectly by both the CPU and the GPU. By sharing the map, the system entirely eliminates the need for slow page fault emulation. This shared visibility drastically alters the performance impact when there is data contention between processors. Contention is now resolved at an ultra-fine cache line granularity. Rather than exchanging massive megabyte-sized pages, the CPU and GPU simply exchange the exact bytes they need, eliminating the bandwidth tax. To handle larger data movements efficiently, these systems rely on an intelligent routing engine called access counter migration. The hardware inherently tracks access frequency for specific memory pages, automatically placing physical pages near the most active processor. Hardware coherency transforms memory from a micromanaged bottleneck into a self-optimizing pool, finally allowing data delivery to match the speed of the streaming multiprocessor. This schematic shows the Blackwell GB203 GPU architecture, synthesizing these micro-level innovations. On the compute side, it relies on unified CUDA data paths and dense FP8 tensor cores. On the memory side, it eliminates PCIe page fault bottlenecks through hardware coherent unified memory. The 2- to 3-fold increase in inference throughput results directly from these structural shifts: unified compute data paths and hardware coherent memory. For developers, this dictates a practical change in methodology. The practice of writing explicit code to manually control every memory transfer is becoming obsolete. Programmers should use performance hints to provide metadata to the system, but must learn to trust the hardware coherent architecture to handle physical routing on the fly. This creates a frictionless state of operation. The hardware runs at maximum utilization, unburdened by idle silicon or data gridlock. The shift from explicit code-level memory management to seamless hardware coherency represents the true maturation of the AI data center.